Ladies and gentlemen, welcome here. Thank you for coming to this special event with Dr. Alexandra Lockwood. We are very, very excited that you're here with us. I would like to say a very big thank you to the US Embassy. Would you like to say a couple of words?
Sure, thank you. And so good evening. Thank you all so much for coming today. It's so nice to see people who are interested, active, involved, interested in the scientific community. We're so thankful to you and your organization and to NASA for bringing us Dr. Alexandra Lockwood. Thank you all so much for coming.
Oh, that's a feedback.
That's not my good side right there. I have had the pleasure to spend 2 days with Dr. Lockwood, and I will be with her again as well. We're so excited that she is here to talk about science and all the wonderful things that involves. So if you haven't visited our embassy before on Facebook, Twitter, or Instagram, that's my plug to follow us, because we always have interesting and exciting things going on. And we welcome you to that. So please welcome.
So I'd like to welcome Dr. Alexandra Lockwood. And we will say a couple of words here, but then we will cover the next room to start the presentation, like I explained before. Dr. Lockwood, please.
Hi, it's very lovely to be here. I've really enjoyed a couple of days in Cyprus so far, and I'm looking forward to speaking with you all. We will be around for plenty of time after I give some remarks and tell you a little bit about the amazing telescope that I've had the privilege to work on. So I will speak with you soon. I'll just be in the other room.
So ladies and gentlemen, welcome here. It is a great honor to have here with us Dr. Alexandra Lockwood, all the way from the USA, all the way from the heavens of NASA. So I will give you a very short presentation for only 5 to 10 minutes, and then the floor goes to Dr. Lockwood. I would like to ask the embassy if you want to say a couple of words too.
Sure. So good evening, everyone. My name is Elaine Kaplos. I'm with the US Embassy. We're so excited to see so many people here who are interested in science, who are interested in what you do. Thank you so much for hosting us. This is
Thank you too.
An honor for us to welcome Dr. Alexandra Lockwood. I've had the pleasure of being with her for a couple of days already. I'm so excited to learn about how the young people in the audience one day will grow up and themselves work for NASA, just like Alexandra. So excited to learn more. Thanks for coming out tonight. We look forward to an interesting discussion. Thank you so much.
Thank you. Before I get started, I'd like to ask Kostas to ensure that the audio is well heard in the next room. Please confirm, and if everything is go, we will start. I'd like to also say a very big thank you to New Horizon, our Turkish Cypriot friends that are co-organizing this event. It is very important to say the following. From the sky, there are no borders. From the sky, we are one planet, and we're all humans. And having our country divided is not something that we space scientists want. So I'd like to ask if you want to say something. Please. A big thank you. I'll pass over to you my microphone.
Thank you. Should I hold it or?
Yeah, you can put it on.
Thank you. Welcome, everyone. We are just a few members from New Horizon from Cyprus. It's an honor, and thank you very much inviting us also and organizing Bicommunal Science. As you said, Cyprus has no borders, universe has no borders, science has no borders at all. So we are one Earth, we are all human, and we are so proud and very honored to be with you here. Thank you so much.
Thank you so much.
Thank you.
Thank you. So, Costa, we're okay? Let's go. Yes, the delay is part of the game with YouTube. So, as I said, this is an event that is organized in cooperation between the US Embassy, NASA, the Cyprus Space Exploration Organization, and New Horizon. So, let's see what I'm going to show. Oh, does it want to change slide? No. Because maybe we need to do that. There. This is a short video we produced with material from NASA. Yes, it is CGI. For those that say that everything from space is CGI, no. We use CGI in order to highlight the beauty of what's out there. But all you've seen here is material that was produced, the original material was produced by the Hubble Space Telescope. And I want to say a couple of words about the Hubble Space Telescope, the predecessor of the James Webb Space Telescope. So, oh, I seem to be going, oh, it's playing games with me. Yeah. So this is the Hubble Space Telescope. And as you can actually see, the size of this one in comparison to the James Webb Space Telescope is very big. You have here the lens of the Hubble. This is the lens. That's a person there standing, and that's the Hubble. And this is the James Webb Space Telescope with this massive lens. So you can imagine if these wonders that you see here, and actually it's downwards, I made a mistake myself. So if these wonders that you see here, the Orion's Nebula, actually it's this one that I wanted to highlight. No, it's in the next slide. This is from a supernova. All these are from the Hubble, but the most important image for me from the Hubble is this one here. That's the pillars of creation. This is a nursery where stars are being born. So you see all these little dots here, especially that there, and all this here, that's where stars are being born. This is the awe and beauty of what was uncovered by the Hubble Space Telescope. And imagine what Dr. Lockwood will present now from the amazing and much bigger James Webb Space Telescope. So you may have seen in the previous slide, this image here. We've used that in the log of CSEO because we liked it that much. So we as organization explore space, NASA explores space. Why? Why do we spend billions in space exploration? Many people say that we have too many problems down here on Earth. And that's exactly the point. We are natural explorers. From that age, we explore the environment. And what we discover is exactly what comes to help us here on our planet. It creates technologies. Some of those technologies are the ones that we can't live without. Telecommunications, GPS. Can you imagine airplanes being able to land in fog? No, that wouldn't be possible. In fact, in the past, we had accidents because of fog, like in the Tenerife. So space has become a great necessity for our life down here on Earth. But most important, with what's happening right here, right now, which is climate change, the depletion of resources on our planets, it is space that brings to us solutions to make sure we have prosperity and a sustainable future. Without further ado, I'd like to give the floor to wonderful Dr. Alexandra Lockwood. Thank you so much.
I don't know how to follow George. He's such a good speaker. He speaks so well. I'll have to take notes.
We're ready.
Okay.
It's down as opposed to up. I made a mistake.
Mistakes are allowed. We do them all the time at NASA. It's true. Actually, I was giving talks to the schools earlier, and somebody asked me if NASA had ever made a mistake or failed in space. And I said, yes. 3 months ago, we sent 2 things to go land on the moon. The first one blew up. The second one landed on the moon and then fell over. Good thing James Webb did neither of those. Or else I would not be out of a job. Okay. So I'll tell you just a brief overview of what NASA does, because we do more than just the universe. So NASA studies all of the things that are out there, including the things that are under your feet. We have a huge Earth science department. We do study climate change, and we're very dedicated to protecting life on Earth, including informing, change to make it better. We study our local neighbor, the sun, and next year we actually are launching 6 missions to study the sun. We are coming into a time in the sun's life cycle where it's going to be very, very active, have lots of activity things coming off of the sun. So we want to study it and its effects on Earth. We study everything in our solar system, planets, asteroids, comets, and we study everything beyond. Planets, stars, galaxies, nebulae, dark matter, dark energy, you name it. If you can name it, we study it. If you can't name it, we probably still study it. So we're going to talk a little bit today specifically about the astrophysics missions that NASA sends out into space. We have many. They cross all wavelengths of the electromagnetic spectrum. But today we're specifically going to focus on Hubble, which George gave an excellent intro to. We didn't even plan it. And then the James Webb Space Telescope. The James Webb Space Telescope here, which we just launched about 2 years ago. And then end with some future satellites, one not even on here yet. So, as I said, we'll start with Hubble. Hubble was launched in April of 1990, so it is older than several of you in this room. And it has really changed the world's perception of astronomy. It has changed the world's understanding of the universe. We've made discoveries like the universe is expanding. We've made discoveries like there are other planets out there. And we've even, we've made discoveries near and far, and really Hubble revolutionized astronomy. If you go out there, and trust me, I've gone out there and asked folks, do you know a telescope? They say Hubble. Although this morning, when I went to the schools, I asked, and they knew Webb more than Hubble. Yes. That was my job. So these are some images from James Webb, or from Hubble, excuse me, Hubble. Give credit where credit's due. You have a star being formed, you have a galaxy, and you have a planetary nebula, which is the death of a small star. But to me, the most interesting picture that Hubble has ever taken is this one, and several like it, because once it took this one, it was like, wow, this is really great. I'm going to do it again and again and again. Now, this picture, to give you some reference, is if you held up your finger anywhere in the sky, you would see this many galaxies and this much material behind it. Anywhere you put your finger, and this is what Hubble did, it looked at a patch of the sky. We had never seen anything. And we've looked at a lot of the sky with several strong telescopes from here on Earth. And we looked at a patch of the sky, of the night sky, that we had never seen anything, a very small patch about the size of your finger, and we discovered hundreds, nay, thousands of galaxies. Now, in addition to that just being really incredible, because it means that if there's 1,000 galaxies here and 1,000 galaxies here and 1,000 galaxies here, you add those all up, you're talking about hundreds of billions of galaxies in our universe, okay? But also, in this one image, we can see the evolution of the universe. Now, from this one image, we can pull out, just kidding. From this one image, I switched around the slides here on myself early this afternoon, so now I'm just catching up. I'm NASA, but I'm not that NASA. So we have different types of galaxies here. All of these things are galaxies that you see. This is a star. You can tell because it's got those sharp edges, and you can actually see the same sharp edges with a slightly different pattern in James Webb images. But if they've got some sharpness to them, we call them diffraction spikes, that's a star. So there's a couple of stars, but everything else is a galaxy. Thousands of galaxies, different types of galaxies, different colors of galaxies. You have some galaxies that you can see the spiral shape in, similar to our Milky Way. You have galaxies that just kind of look like blobs. And if you look really closely, you can see some very faint red dots here. Those are the ones we're really interested in because they're small, they don't have much structure, they're faint, and they're red. And what does that tell us? It tells us that they're really far away. And in the universe, really far away also means really old or really young, depending on how you look at it. Imagine you are here in Cyprus and you took a picture of yourself and you gave it, or you took a picture of your baby and you gave it to your friend and you said, okay, run this over to France. By the time that person got to France running, your baby may be entering school, right? They're not a baby anymore. But the picture you took of them is still of a baby. So that person in France, thinking of your baby, thinking of your child, thinks it's a baby. It's the same thing with light in our universe. Light takes time to travel. It's not instantaneous. It's almost instantaneous from the lights in the room, but the sunlight from the sun takes 8 minutes to get to the Earth. And the further you go, the longer it takes for light to travel. So if light is emitted from a galaxy at the beginning of the universe, as it travels a long, long, long time, a long, long, long distance to get to us, we see it as it was billions of years ago, but it has changed, and we're all the way over here, 13.8 billion years after the Big Bang, and the more distant object is now a very young object. It's a galaxy from the early universe. That's what these are. And how do we know that? They're small, they're faint, they're very far away. They're kind of nebulous. They don't have structure yet. It takes time for things to form structure. So this shape that you see here is much more evolved. This shape that you see here, you kind of see the swirls. It's much more evolved than sort of a globby galaxy. But most importantly, they're red. Because as that light has traveled over billions of years, the universe has expanded. We know from Hubble and recent James Webb, confirmation that the universe is expanding, and it's expanding at an accelerated rate. As the universe expands, the light itself expands with the universe. So not only are we seeing farther, which means we're seeing things that are very, very old from a long time ago, we're seeing the babies of the universe, but They don't look like babies. Now they look like red babies. It's a bad analogy. It breaks down at some point. But light looks redder and when it's traveled farther through the universe because the universe has expanded. It has expanded those wavelengths. And what I say to all my students this morning, what is redder than red? Infrared. So I'm sure many of you are aware here, but just in case you're not, we have many different types of light in the electromagnetic spectrum. You've heard of all of them: radio waves, X-rays, ultraviolet waves, but we mostly see with visible light. That's what our eyes see. That's what our Hubble Space Telescope sees. George showed you earlier a beautiful image that showed you the Hubble telescope and the James Webb Space Telescope. The Hubble telescope was smaller, but it was also silver. What color is the mirror in your bathroom? Silver. Our eyes see visible light. Hubble sees visible light. Silver is very reflective of visible light. Guess what's reflective of infrared light that James Webb sees? Gold. That's why it's gold. People ask, that's why it's gold. No, it didn't cost that much more to make it gold. It cost a lot of money already, don't worry. But James Webb is tuned for infrared light because the light from the galaxies that we see with Hubble has now been stretched over the entire time of the universe, 13 plus billion years, and it looks redder than our eyes can see. So it's infrared. So we had to build a very large telescope, very large because it had to see faint objects, and we had to make it infrared because we needed to see infrared light to be able to detect the first galaxies in the universe. That was James Webb's first goal. The telescope's first goal was to see the first galaxies in the universe. Now, the other really incredible thing about this observatory, in addition to the giant gold mirror, and it is 6.5 meters in diameter, very, very big, is the 70-meter sun shield. Now, normally, when we look at a telescope, including Hubble, it comes in a big tube. You'll go outside later, have the opportunity to look through a telescope. It comes in a big tube. Normally, we use a tube to cover the lenses, the optics, from stray light. Well, this was too big. It's too big to get into the rocket. I'll tell you, we had to fold it up to get into the rocket. That was a whole thing. It was a whole thing. But also, it's way too big to put a whole covering around. So we did our best. We half covered it. We covered the side that faces the sun because the sun emits a lot of infrared. Infrared wavelengths are also known as heat. The sun is hot. When we put something out in space, even 1 million miles away, like James Webb is, we have to block the heat from the sun, or else that would just dominate, right? If you have a bright light source, you can't see anything around it. Try to look at the light, don't actually, but I'm telling you it's true. So we had to block the sun, at least, and the Earth also has a lot of heat, before we could look deep into space. So, you know, I won't go into the specifics. Also, I'm a scientist, not an engineer, so I don't know all of the specifics, but I will tell you that in order to make this thing and this thing, lots and lots of innovation happened, lots of new technologies and things that are being applied in other places today. As George said, there is a new mammogram technology for women based off of James Webb technology. Who knew that was going to happen? None of us, but we did it anyways, and look what good came out of it. So we launched James Webb on Christmas Day. I wasn't with my children, but I was with my telescope, so it was okay. It took 6 months for it to get into space and unfold. This thing is huge. It is the size of this building. And we had to fold it up to get it even into the largest rocket we had, which, by the way, was supplied by the European Space Agency. James Webb is a partnership between NASA, the European Space Agency, and the Canadian Space Agency. And one of the contributions of many of the European Space Agency was an Ariane 5 rocket, the biggest there was at the time. But still, it wasn't big enough for a 70-meter telescope, so we folded it up, and then we unfolded it in space as we sent the thing 1 million miles away. It was a very nerve-wracking time, but I'm very happy to say that it worked splendidly. And I had the pleasure of doing this with it. So it was truly my pleasure to lead the team that came out with the first images from the telescope. Now, Yeah. I still pinch myself. I am very, very, very privileged. So we spent years planning for this. And then we had about 6 weeks between when we got our first data and we put out all of these images. We had to prove to the world that the telescope worked, that it did all of the science that it was supposed to do, that all 4 of our instruments were working and could do all of the different modes that they had promised. And we had to wow. When I first started my job with the James Webb Space Telescope, in my interview, they asked me, somewhat rhetorically, but also a little bit of seriousness, how are you going to make Webb a household name like Hubble? And I took that as my challenge. Now, if you just remember what I said earlier, that I spoke to students earlier today, and the next generation, they know Webb more than they know Hubble. So I really, truly think that I have done my job because Webb is becoming as popular as Hubble. And this is how it started. So these images right here are of Stephan's quintet. This is 5 galaxies. Some of them are together, some of them are further in the distance, but there's several interacting galaxies. To me, it looks like a dragon. I love this one. This is the atmosphere of an exoplanet. We've proved Webb's capabilities and found new molecules. We'll talk about that in a second. This right here is a deep field. The President of the United States liked this one so much, he wanted to share it with the world himself, so I had to give it to him. I was okay. I was okay. And this right here is 2 images of a dying star. Same image, different wavelengths that show you different details. And this one right here is on my dining room wall. This is the Carina Nebula, the most gorgeous image I've ever seen in my life and probably will ever see. And it is of a star-forming region, what George spoke about earlier, one of the most beautiful places in the universe, and also one of the most important because it's where we all came from. My research was about studying star-forming regions and specifically the materials inside them that start to form planets. So that happened about 2 years ago. Since then, we have proven that James Webb can make incredible discoveries in all of the types of science it promised. Studying the early universe, studying how galaxies evolve over the course of the universe, studying how stars and planets evolve, how stars are born, how they die, and how that affects their environments. And studying other worlds, both within our own solar system and beyond. So I'm going to give you some highlights. Early universe. Within a few months of being launched, Webb found the oldest galaxy ever discovered. I have to correct myself because I was corrected by a student earlier and I appreciated it. Webb did not make any discoveries. Scientists using Webb made all of these discoveries. Scientists, people, are the real champion. Webb helped a lot. So, scientists using Webb discovered the oldest galaxies. And you can see here, they're tiny red blobs, even in this picture. So it's a good thing we have Webb, because if we didn't have anything as big as Webb, we couldn't see them. We've also just found a lot of old galaxies. We thought we saw a lot of galaxies with Hubble. Well, that image that I showed you before with Hubble took over 30 hours to take. This one, less than 1 hour. You cannot take an image with Webb without galaxies in the background. It almost got to be annoying because our first image that we put out was just of a single star, and we only wanted to show one star, but there was 1,000 galaxies there, and we just couldn't get rid of them, which is not a bad problem to have. But we have discovered so many old galaxies that we can really start to understand them. So we found the oldest galaxy ever detected so far with Webb, about 300 million years after the Big Bang. But we've also found ones that are 500 million years and 600 million years and 1 billion years and 2 billion years. We have so much data now that we can really start to take a picture of the entire evolution of the universe. So to put it into perspective, with Hubble, we saw if the age of the universe is like a person, right? So let's say the entire age of the universe is about a human lifespan, 100 years, if you're lucky. Hubble saw all the way back to the preteen years, they're ending primary school. Now James Webb has seen toddlers, and it's seen a lot of toddlers and kids in primary school and teenagers. And we can start to understand the full evolution of galaxies because they're different. We are different. You need a huge sampling in order to really understand how the population. And we're starting to get that with Webb. And it's only been 2 years. The discoveries are going to continue to come. You know, they're still putting together all of the pieces, but I'm very excited. But this is not my science, so I can't go super deep into it. But it's very exciting. Speaking of how galaxies change over time, one of the things that we found is the earliest protocluster. So something that's very unique about galaxies as opposed to stars or planets or nebulae is that galaxies tend to cluster. We see them in groups. They like to have friends. Our galaxy is part of a cluster called the local group. We have several galaxies nearby. With Webb, for the first time, we found a very early cluster, which tells us about how fast galaxies evolved in that early universe. Not only did galaxies form, but they formed friends and groups very early on. And that tells us about where there was dark energy, where there was dark matter, for all of that to aggregate onto. So that is pretty cool. We've also seen thousands of galaxies that we're still, digging into to understand what they look like, what they mean, what kind of stars are forming there, how does the gas and dust change as a galaxy evolves. So just a sampling of all of those different galaxies. One of the new discoveries with Webb is that with nearby galaxies, we can actually start to see the bubbles of the stars are forming. So we've been able to see stars in galaxies with Hubble. Now we're able to see more detail around the stars and see them carving out bubbles within these galaxies, which is incredible detail. We've seen that in our own local galaxy, but never in other galaxies. Wrong way. So this is my favorite. This is also the pillars of creation. George knows exactly what he's doing. He got Hubble, he got the sizes of the mirrors, he got planet, star forming regions, and he got pillars. Like he knows everything. He knew what I was going to talk about, and we didn't plan it. But this is the pillars of creation. It looks slightly different from what George showed because he showed a larger view. I'm zooming in on a very special part of it. 3 fingers, it looks like. This is all the exact same area of the sky, the exact same picture, but it looks different. Why? Because it was taken with different wavelengths. You may have broken a bone and gotten an X-ray. You may have gone to the dentist and gotten an X-ray. We use X-rays to see inside our bodies. They are a different wavelength of light, and they give us a different view of our body. We use different wavelengths of light in space to get different views of the same object. This is the gas in the pillars of creation. So the bright stuff is the gas, and the dark stuff is dust that you can't see through. It just is opaque. You go a little bit longer wavelengths, very near infrared, you start to see through that gas and dust, and you see stars. These are the stars that are carving out all of that material in those pillars of creation. It is a star-forming region. Stars are forming. We are starting to see them. Now, these are 2 different wavelengths of light from James Webb. We are seeing dust in both of these different types of dust. So these are what we call polycyclic aromatic hydrocarbons. Doesn't really matter. These are complex organic molecules. This is longer wavelength dust like hard rocks and bigger pieces of dust. So same object, 4 different wavelengths, 4 different views, and now we can study everything. You could not understand the human body if you did not understand the bones, the muscles, the skin. You can't understand a star-forming region if you don't understand the gas, the dust, and the stars already there. So we put together these pictures, and then to highlight something about the other worlds that we've studied so far. So we've looked at almost all of the objects in our solar system that are outside of the Earth's orbit, because it has to look away from the sun. And one of the most intriguing and beautiful, I think, since we're talking about how beautiful the images are, is Jupiter. We've discovered extremely high jet streams on Jupiter, and using different wavelengths, we can actually see into the atmosphere of Jupiter. Just like when you use different wavelengths, you can see into the human body. So we're starting to piece together the atmospheric chemistry of Jupiter, how fast things are going. And a lot of times we use Jupiter as kind of a middle ground between what's going on in our Earth's atmosphere and what's going on in atmospheres of other planets, which Webb also studies. This is a hot Jupiter, a very large planet, larger than Jupiter, that we've discovered. We discovered before Webb, but we've looked at it with Webb and found new molecules for the first time, the first detections of molecules ever made on other planets, including methane and carbon dioxide. Carbon dioxide and sulfur dioxide for this one. So carbon dioxide and sulfur dioxide, these are the first detections we've ever made of them. They're very interesting molecules, especially because as humans, we breathe out carbon dioxide. So we want to know if there's carbon dioxide elsewhere, because maybe it was created by a living organism. So to talk a little bit more, because I know it's of interest, about the search for life, one of the things that Webb is doing, pushing the boundaries of, is looking for what we call biosignatures. So a biosignature is either something that we associate with life. So for example, we breathe out carbon dioxide. Maybe other living things breathe out carbon dioxide too. So maybe if you see carbon dioxide in an atmosphere, it is an indicator of a living thing on that planet. However, carbon dioxide gets really readily made in the atmosphere through other chemistry. But one thing that doesn't is dimethyl sulfide. So this detection that was really interesting a couple of months ago, but has yet to be confirmed, which is why I take it with, caution, is a atmosphere that we believe has methane, carbon dioxide, and dimethyl sulfide. Using the model, this was the best fit, including these molecules. Now, there's two takeaways here from this chemistry. One, that there could be ocean on this planet. And two, that because of the presence of dimethyl sulfide, you can't make that naturally from chemistry. But what does make that on Earth is phytoplankton. So the presence of this molecule, and it is still a tentative presence, we are doing more research to follow up to confirm, but the presence of this, we only know to come from life. Very exciting, very interesting, but as scientists, we question everything. So we're not making any grand assumptions yet. We're excited, but we're going to do more research and follow up. And this is another big planet, K2-18b. It's not quite as big as Jupiter. It's called a sub-Neptune, but it's much bigger than the Earth. So we don't think it has a solid surface. It may have an ocean, but it doesn't mean it has a solid surface. However, Webb is pushing the boundaries of the kinds of planets that we can see. And indeed, just 2 months ago, Webb for the first time detected what we think is an atmosphere on an Earth-like planet. So right here is, the name of the planet's not on here. It is 55 Cancri E. This is an example of the dips of light from the star that we see when a planet crosses in front of it. The US just had a total solar eclipse. You guys are going to have a partial solar eclipse in a couple of years. It's very exciting. But that's when the moon crosses in front of the sun. When we look at other stars, we can see planets crossing in front. It's called an eclipse or a transit. And we can see when the planet goes in front of the sun because the light from the sun drops down as it gets blocked. We can also look when the planet goes behind the sun because there's even less light. It's a lot of math. I'll explain it to you in detail later if you want. But using this thing, we can figure out how hot the planet is. And we can figure out if the planet has different temperatures on different sides. Just like on Earth, we have a day side and a night side. And it's hotter on the day side and cooler on the night side. But it's not as hot and cold as it could be because we have an atmosphere that buffers us. So using this technique, at first, Webb looked at another planet we were very interested in, TRAPPIST-1b, and found that it has no atmosphere, that it's very hot on one side, very cold on the other, no atmosphere. And then just recently in March, we found a planet that does have an atmosphere, that is also the size of Earth. So we have taken this telescope, we found where stars are forming, we found where planets are forming, we've looked at planets that are like ones in our solar system, we've looked at planets that have new things that we've never seen, but remind us of some things we've seen on Earth. And we've looked at planets that are much more like Earth, but we're still learning about them because we can't quite get into their atmospheres like we could here, because this is a bigger planet. Bigger, more light, more to analyze. This one, we're not there yet. But we're planning on being there in maybe 20 years with NASA's next observatory, the Habitable Worlds Observatory. So the future of NASA, the future of astrophysics at NASA, I should say, is right here with the Habitable Worlds Observatory. We have not figured it out yet, so that you don't see a picture of it, but this is a infographic, a diagram of all of the worlds that we could study. And we are planning the next observatory, the next revolutionary observatory, to find us another Earth and potentially life. So with that, I will say thank you. And I'll take a break.
I want to say a very big thank you to Dr. Lockwood. And you just reminded me of something. 2 years ago, it was July. It was the day that we saw the first images, your first images. And I won't forget that we filled the room next door, the same chairs, different layouts. And we were selected by NASA to be one of the first places around the world to share the celebration, to share the images simultaneously. And to have you here with us today, I can't express my enthusiasm. Thank you so much.
We want to do a few questions here before we spread out.
So what we're going to do is we will take some questions from the people, the media. We will go next door and make sure that we engage all the guests equally. It would be unfair to stay just in this room. But let's first take 2 questions from the public and then take more questions from the media. We should wrap up within 5-7 minutes or so in order to give the same chance to the audience next door. So, any hands? Yes.
I'm interested in the history of the Space Telescope. And if I understand, the telescope circles around a crash point, and at the same time, circles the same period as Earth. Is that right?
Yes, yes, it does. So it both orbits the L2 Lagrangian point and it orbits the sun with the Earth. So because the telescope needs to shield itself from the light of the sun and the infrared light from the Earth, which gives off a lot, this telescope is always facing away from the sun and the Earth. To do that, it sits at a quasi-stable point that is called the second Lagrange point, and it goes around the sun with the Earth. So the Earth is always behind it, which is then in front of the sun, always. So that's one orbit that it does generally. But in order to stay at a quasi-stable location, it goes around. So the actual orbit of the telescope is going around like this as it goes around the sun.
But by station keeping, what do you mean by station keeping? What is doing to avoid to go further than 1.2?
Yeah, so again, quasi-stable. So we can't be right there. We have to go around it. But even then, we start to be pushed a little bit by the mutual gravities of the Earth and the sun. So we have to just push ourselves back. And it's only every 3 weeks. So that's good. But that's called station keeping. It's just getting back in line. Yep.
Gentlemen there.
The discovery of the early universe, very exciting. That opens up some discussion on the Big Bang. Can you speak to that?
I wish I could speak about the Big Bang, but first of all, I am not a cosmologist, so I'd probably get it wrong. And second of all, most of the information that we have, and I say most because gravitational waves, but most of the information we have comes from light from the universe. And prior to about 400,000 years after the Big Bang, there was no light because everything was a very solid, dense mass, and literally atoms didn't form to let out the light. So we cannot see past, we literally could never see past 400 years after the Big Bang. And so to get at the Big Bang is all theoretical, and that is beyond me because I'm not a cosmologist. But so James Webb is going to be a 10-year mission. It's 5 guaranteed, and then it's a 5-year mission, but it's been built for 10 years. But there's a much longer possibility due to fuel. So there's 10 years of fuel aboard, and we'll just see how the instrumentation goes.
Okay, so what we're going to do is, because you were lucky to have Dr. Lockwood in person here. So we're going to move next door now, unless, is there media here that wants to ask any questions? No. So we're going to move next door, okay? So let's all go next door to make sure that the people that were in this room have the chance to ask more questions, just to be fair and balanced, okay? So let's go next door.
Big telescope. Infrared heat. We found the first galaxies in the universe. We are understanding how stars form. We are finding lots of molecules that we've never seen before, and that are really giving us some insights into what different types of planets are out there and what different conditions exist. And we are comparing them with things on Earth to see what could maybe be hospitable to life, but we still have a long way to go and another observatory to build to really get to answer. But James Webb has well outdone itself already, and probably will keep going for another decade. And yeah, so very good, very good. I'm a big fan.
The only thing I want to say from like an outtake from what you said, which I thought was, it actually got my hair like standing, like goosebumps. There is a planet, K218b, and that exoplanet has shown the presence of methane, CO2, but also DMS, which is dimethyl sulfate, which needs to be checked again, because if indeed this exists, phytoplankton, as we say in Greek, which is in the oceans, is the only thing we know on Earth that creates that. Just the idea that when that is checked again and again, and we're certain of that measurement, my hair are standing that we are not alone in the universe, but we're not there yet. We're not there yet, because that has to be verified and verified again. We're not going to make a mistake of such an announcement, because such an announcement, oh my God, is groundbreaking. Okay? And the other one that I really liked was, there's a planet of similar size to our planet that the James Webb Space Telescope, I said it, has detected atmosphere. So we are getting closer and closer to amazing discovery. Actually, we had amazing discoveries, but to maybe that amazing discovery of, are we or are we not alone in the universe?
Good.
So thank you, everyone.
Just wanted to say, there's more, don't leave. But on behalf of the U.S. Embassy, thank you so much, for hosting us, for hosting Dr. Alexandra Lockwood. Thank you for being here. This is, I think, the fourth time I have heard her speak, and her speeches have been tailored to the audience. I've learned something new each time. I have felt small and big and educated and uneducated, and all the emotional spectrum. So thank you for bringing all that out. For all of us, I know I'm not alone. I wanted to say to you that, the U.S. Embassy knew this about what happened, and that's why we brought her. I wish I could say that was true. By some cosmos, it worked, and you sent something out into the universe, and she came to us. So that's very special for us. Right. Thank you.
You actually moved me and you left me speechless. And I want to say also a very big thank you to each one of you, but also to our partners at this event, New Horizon. Where are you guys? There. Thank you so much. And I want to say a big thank you to you. Give you a hand. You will notice that some of us, not me, I actually have a NASA one here, thank you. So some of us have got a round button that says, I am an expert, come and talk to me. And some of them say, I'm not an expert, don't come and talk to me. Don't speak to those. I'm only kidding. So if you want to ask questions after this, regarding the exhibits, regarding anything you may want to ask, we have loads of experts here. Do you want those experts to raise your hand so that people can see you? 2 of them here, and there's a few more at the back, okay? So enjoy the evening. Thank you so much for coming here today. Thank you. Thank you.